Flood inundation modeling commonly uses a bottom-up simulation process that utilizes feature engineering and software such as HECROS. This process has been developed by the Army Corps of Engineers and has been the regulatory standard for decades. However, this process is resource-intensive, which limits the frequency with which flood modeling can be performed. Bottom-up modeling also relies on a specific set of data inputs, potentially excluding other significant variables. As the climate changes, rain events are quickly changing in frequency and intensity. At the same time, the built environment is always in flux. Both changing forces require a flood prediction model that can be performed more frequently and incorporate a wider set of data inputs. Top-down flood risk modeling can be a powerful tool for planners, FEMA, the private insurance industry, and even the real estate industry, and that it can be performed relatively easily and much more frequently than bottom-up modeling, and incorporates a much wider set of big data inputs. Our top-down model looks at several big data sets that are publicly available for most urban areas in the US and Canada. We trained the model using Calgary in Alberta, Canada. The resulting model was then applied to Cincinnati to test the predicted outcome of a similarly catastrophic flooding event in that city. To train the model, we used flood inundation from a 2013 flood in Calgary. The outline of the flooded areas was traced into the model. A grid with a 200 by 200 meter cells sizes was applied as a fishnet to the map in order to encode the data. Each cell represents roughly a city block. Several features of the landscape were engineered into the model. The top 4 features that we used included elevation, which was taken from LiDAR data, land cover, which was processed from satellite imagery, distance to steep slopes over 15% grade, as well as sub-watershed basins. 10 factors in total were encoded into the initial model. Logistic regressions were performed on each of the factors as they relate to flooding. The results of the regressions show the relative correlation between the various factors in flooding. We worked through multiple iterations of models, manipulating which variables to include and which to omit. We landed on 6 variables, which included impervious developed land, grassland, forested land, elevation, distance to steep slopes, as well as sub-watershed basins. This chart shows the accuracy of our model. It is perhaps too overfit to the conditions of Calgary and is therefore not great at predicting across different contexts, and therefore would not be great at predicting in other cities. We know the model's accuracy because we randomly set aside 30% of the data to test the model against, and we used the remaining 70% of the data to train the model. This approach, called partitioning, allowed us to assess the accuracy of the model as we adjusted the inputs. This helped us to achieve a more accurate model. As you can see, the model did a fairly good job at predicting flood inundation probabilities, and therefore risk of flooding in Calgary. The pink cells represent the actual flooded areas, and the purple cells represent our model's predictions of high-risk flooding areas. The same model was applied to Cincinnati using the same data inputs. The resulting risk map shows that this model is predicting flooding for huge swaths of the city. This map shows the major limitations of this particular model and for top-down modeling in general. Since this type of modeling takes into account only the data encoded into each cell, it fails to account for the systemic interrelated nature of hydrology. For example, there is a massive barrier dam located where the Mill Creek empties into the Ohio River. This dam prevents the Ohio River from flooding back up into the Mill Creek Basin. This dam causes flood inundation to occur far differently than what this model predicts for. The top-down modeling approach does not take into account physical features like this dam, which is a major shortcoming of this approach. Further development of this model will greatly benefit from more advanced physical feature engineering. Also, encoding upstream features into each cell is crucial for making the model accurate. For example, knowing the impervious content upstream of a property has major ramifications on whether that property will flood. Though this model is not quite robust enough to be useful in a regulatory setting, it represents a proof of concept for a different approach to flood risk mapping.